always does these days.
Okay, well, are there any questions before we start? Yeah, go ahead.
I think it's the third question on the homework. It asks you to obtain a 4-level pipeline filter. Do you want us to use scattered or clustered, or does it not matter? Or
Well, okay, yeah, I don't have the problem with me, but it's a second order filter.
yeah.
Yeah, so, yeah, just write down or try both and see, try cluster and see if it is stable or not. Okay, where are the poles?
3/4 E plus or minus J pi over 4.
Yeah, okay, so, yeah, so I guess without thinking, I can say the intent is to use scattered.
Okay.
Yeah, I mean, if the pole is at 3/4 plus or minus, for sure, for two-stage pipelining, you cannot get stable filter. You cannot, okay. So,
Why is that?
well, that's because the sum of the roots is 1.5, minus 1.5.
Oh.
And then when you multiply to get clustered, you will multiply the polynomial 1 plus 1.5 z to power minus 1, and that 0 and cancelling pole are outside the unit circle. Right, okay, you have to look at the sum of the roots. Okay, any other questions? So we were talking about scaling and round-off noise. Scaling and round-off noise are two different things, two different objectives. Okay, the main objective of scaling is to make sure that all the state variables have same power so that we can allocate same word length to all of them. So when we scale a filter, it doesn't mean it has less round-off noise. Round-off noise is something else. Round-off noise is simply the effect of the round-off noise source propagating to the output. So that's kind of our main focus today. But before I get to round-off noise, let's just, so I can complete the computation of the K matrix. So we were talking about the state covariance matrix K. And so we spent quite some time talking about the K matrix, and we defined the K matrix as the expected value of the state variable when the input is a random signal with a 0 mean unit variance, state times its transpose, and the state variable we saw the transfer function or the unit sample response. The unit sample response, to compute the unit sample response, we computed the transfer function from the input to the state variable, and the unit sample response was a to power n minus 1b, and the state variable with random signal un as the input was that quantity, and that's how we got this equation for K matrix. So where I stopped, I talked about the Lyapunov equation. So where I stopped here is how to compute that K matrix. Okay, so how to compute K matrix. So let's spend a little time how to compute. Okay, So we can compute K very quickly using an iterative process. Okay, so here is how it works. Initialize certain f is equal to A and initial K is B transpose, and then iterate until f approaches 0. It won't be exactly 0, but you can use some small number as a threshold. Then we iterate using this. So K is equal to previous K plus F previous K F transpose, and then update F is equal to F squared. Okay, so that's really the iterative process. So we initialize F to be A, K to be B transpose. So you can think about when we start in the very beginning, we start with one term K, the first term B transpose. Okay, and then so what will be, so in the first iteration, what will be K? So iteration 1, K will be equal to previous K B transpose plus F was A, F was initialized to A, so plus A times previous K B transpose times F transpose, which is A transpose. Okay, so and then we initialize F to be previous F squared. Previous F was A, so F squared is A squared. Excuse me, F squared is A squared. Okay, so that's iteration 1. Now you can see now we have two terms. We have the, so if you look at this infinite sum, so we have two terms now, B transpose plus A B transpose A transpose. Now in iteration 2, we will show the first initialization at one term, then we have two terms, and then we iterate, we get 4 terms, then we iterate, we get 8 terms, and so the number of terms keeps doubling with every iteration, and at same time F, so after, okay, let's just continue one more iteration. So K is going to be previous K, which is these two terms, okay, so B transpose plus A B transpose A transpose plus F, so now F is A squared, so A squared times this whole thing post multiplied by A squared transpose, so I get A squared times B transpose times A squared transpose plus A squared times A, which becomes A cube, B transpose times A cube transpose. Okay, that's, so now we have 4 terms, and F now becomes previous F squared, which is A to power 4. So now we have 4 terms. After next iteration, if you keep going through that process, we get 8 terms, and F is going to be A to power 8. So we keep doubling, and as long as the filter is stable, all the eigenvalues of A will be the poles of the filter, which will be less than 1 in magnitude. And at some point F will approach 0. If we keep taking the square, A to power 4, A to power 8, at some point F will approach 0, and you can set a small threshold, say 0.001 or something like that, and you can stop when you reach that small number. So that's the iterative process of computing K, and usually 4 to 5 iterations should be sufficient to compute K. Okay, so that's so you can see that what we want really is that infinite series, and at some point it can be truncated so that the subsequent terms don't really contribute very much. So that is the iterative process to compute the K matrix, and you will have experience with some of that doing homework to compute the K, and what we will talk about next is the W matrix, the Roundoff noise matrix. Okay, so I am not going to go through that more, but so that's kind of the idea. So let's spend a little time now talking about Roundoff noise calculations. Okay, so what we are really interested in is to capture the effect of a Roundoff noise source. So we assume that every multiply add introduces Roundoff noise. Okay, so that's kind of our assumption. So means that if I have certain signal multiply and add, okay, so then if this was, for example, 10 bits, the coefficient was 10 bits, let's say this is 19 bits, and let's say another 19 bits. So this is now rounded back to 10 bits. So in the hardware, the multiply add, this whole thing is computed and then rounded to 10 bits. So this can be modeled as certain Roundoff noise EN. So the process of rounding the 20-bit result back to 10 bits, okay, so I can model that. It could be 19 bits, so maybe this came from another multiply operation, which is fine. So yeah, okay, we could have another multiply operation here, and 10 and 10. Okay, so and then this is also 10. So and the whatever was the rounding error, we capture that as this EN, which is an error signal. And once again, we'll make certain assumptions. So rounding operation is introduced after every multiply add. So in this case, even if there are many multiply adds, many multiplies going to the adder, still we can model that as one Roundoff noise. We don't need, so okay, the other noise model. So if I assumed the noise model to be right after multiply, then I would have one noise source here, one noise source here. And effectively, then this would be, this noise source effect to double. And we don't want that. In hardware, in any case, we are performing these multiplies and add operations at the same time. So that's where the Roundoff noise is introduced. It's introduced after every multiply add. Okay, Roundoff noise, so let me make it clear. Roundoff noise is not introduced after multiply. Okay, so it's introduced after multiply add. So in other words, the Roundoff noise is not here, but after the add. Okay, so that's kind of what I'm trying to say. Okay, so
is there any specific reason for defining the noise like that?
Yeah, there is, and so when we implement these multipliers in hardware, whether you are using any kind of okay, so the question, those of you on Unite, the question was, is there any reason why we model the Roundoff after add operations? So in the hardware, if it is any kind of multiplier, whether it's both recorded multiplier or Wallace tree multiplier, we are operating these together and we are adding at the very end by something called vector merging adder. And if that word doesn't mean very much, well, that's, all of that is topic of next semester class. So I think we'll talk about vector merging adder in the next semester class. So the two, you can think about two of these operations are merged. Two numbers are merged to one output result. Okay, so how does the Roundoff noise source propagate to the output? So that's really what we want to understand. So So to start with, this may be a review for some of you who took certainly those of you who took DSP class from me, and there are few of you in this class. If we have a Roundoff noise source En, and the unit sample response from that error source to the output is H of n, and we will assume this to be zero mean, variance sigma squared or sigma E squared. Sigma squared, that's fine. Or sigma E squared. Sigma E squared is fine. So what is the error at the output? What is the error at the output? So if there are no other input signals, when we are computing the effect of this Roundoff noise at the output, we set every other external input to be 0. We set all other Roundoff noise sources to be 0 as well. So there are certain other assumptions that I didn't talk about, but so all Roundoff noise sources are independent. So that's why we can apply superposition and compute the effect of Roundoff noise from one source at a time and finally add them up. All the Roundoff noise sources are independent. Okay. So Yn is going to be summed over all k, hk, En minus k. Okay. And then y squared n is going to be summed over k. So if I take this times itself, the process of doing that is to take two summing indices. So that's one y, and to write another y, I use a different summing index. And then we can have the double sum k equal to k and l, hk, hl, and En minus k, En minus l. And then expected value of y squared n is going to be expected value of this. Expectation of the sum is the sum of the expectation. So that's the expectation of that. And this quantity here is sigma E squared delta k minus L. Okay, why is that? When k is not equal to L, En minus k and En minus L are different quantities. The expected value of this and that is going to be expected value of this times expected value of that. Expected value of E is 0, so that's 0 times 0. If, however, k is equal to L, then this becomes expected value of E squared something. The time index doesn't matter, expected value of E squared. And that is going to be the variance sigma E squared. So this is 0 when k is not equal to L, and when k is equal to L sigma E squared. So when k is equal to L, the double sum becomes single sum, and hk times hk becomes h square k. Okay, so that is times sigma I square. So that is the error. So the error at the output, the expected value of the output squared, expected value of the output squared is going to be the variance of the error En multiplied by sigma h squared k. So that's kind of what we are really interested in. From every noise source, we need to compute the unit sample response, and then we need to compute the sum of h squared k for all k, and we do that for every round of noise source, add them up, and that's the total round of noise at the output. Of course, this can be, if there are 100 state variables, this can be very, very involved, and that's where the W matrix comes in. And W matrix, again, we can formulate a Lyapunov equation for the W matrix, and like the K matrix, we can compute the W matrix within using a similar iterative process. Okay, so there are ways to compute that. So that's really why we are interested in the sigma h square k, which is the hk or hn is the unit sample response from the error source to the output. Okay. How many of you have gone through this in your previous DSP class? Okay, that's fine. So this may be a good time to work out an example. So this is an example from a prior exam, prior DSP exam, but that's still okay. So let's so this some previous exam, DSP exam 4541. So we have a signal flow graph, and we want to compute the round of noise. So let me just see if we can work that out. So this is xn, and we have multiplied by 6 delay multiply by 1 by 12 Okay, so in this filter, although there is no add here, still we have to round the multiply, right? So ideally speaking, if we were adding something else, then we would wait until we add, but there is no add operation here, but still I need to put that into this delay element or flip-flop. What we see here as z to the power minus 1 is really the number of flip-flops or delay elements in the actual hardware. So if it was a 10-bit word, then this would be 10 flip-flops. Okay. So we can assume the round up noise after this multiply add. Okay, so this multiply add. Okay, we can assume that is E1N. We can assume this one here is E2N, and then this multiply add E3N. Okay. Okay, so those are the three noise sources. And then we are interested in computing the transfer functions from the three noise sources to the output. So when I compute the transfer function from E1 to the output, set the input to be 0, set E2 to 0, set E3 to be 0. Just take one external input E1. So obviously this path disappears because E3 is 0, input is 0. The transfer function from E1 to the output, so now the output node is same as here. So what will be, so the forward gain, so that will be 6 forward gain by 1 minus the loop gain. So 1 minus the loop gain is 6 times z to power minus 1 times 1 by 12. Okay, so that is the transfer function from E1 to output, E2 to output. What will be the transfer function from the, so again we set E1 to 0, input to 0, E3 to 0. So one could easily think that the transfer function from E2 to the output is 1. The transfer function is 1. But that is not the case. And the reason that is not the case is because this is where we have E2. And then we have that loop here. Okay, so that loop with gain half z to power minus 1, 6 times 1 by 12. So all these are 0, but there is a self loop here, and that is output y. Okay, so again, one would think that it should be 1, but it's not. You have to take that as 1 over 1 minus the loop gain. So the forward gain from here to the output is 1 over 1 minus that self loop, half z to power minus 1. And from E3 to output, so to compute that transfer function, set E1 equal to 0, set E2 equal to 0, set input x to be 0, and the forward gain is 1, the loop gain 1 over 1 minus loop gain, which is still same thing. Okay. All right. So now we can compute let's start with E3 to y. E3 to y can be written as 1 plus half z to power minus 1 plus 1 quarter z to power minus 2 plus 1/8 z to power minus 3. I'm using the geometric series 1 over 1 minus x is equal to 1 plus x squared plus x cubed up to infinity. And this, of course, it converges only magnitude of x is less than 1, and here magnitude of x is half, so that's okay. Half times z to power minus 1. And magnitude of z is 1, it's on the unit circle, so that does satisfy that constraint. So sigma h E3 to y squared is going to be 1 plus half squared plus 1 quarter squared, half squared, plus 1 quarter squared plus 1/8 squared. And that is a geometric series, and that's going to be 1 over 1 minus r. R is half squared, 1/4, so that's 1 over 1 minus 1 by 4, which is 3 by 4. Reciprocal of 3 by 4 is 4 by 3. Okay, so the sigma of h E2 to y squared n over all n, what will be that value? So that's going to be 4 by 3 as well. Well, these two transfer functions are same. What will be sigma h E1 to y squared n for all n? That's going to be 6 squared times 4 by 3. Okay, so that's 6 times that, you take the square, 6 squared. So that's going to be 36 times 4 by 3, 12 times 4, 48. 12 times 4, 48. So total round of noise, sigma y squared, is going to be 48 plus 1 and 1/3 plus 1 and 1/3. So that's going to be 50 and 2/3 sigma e squared. So that's going to be the total round of noise at the output due to the 3 noise sources. Okay, any questions about this?
So this noise parameters, is it for like telling, is it a measure of performance of the hardware or like of how good is this output signal?
Yes, exactly. It's how good the output signal is. So yes, that's what it is. It is about the signal to noise ratio at the output, and absolutely, yeah. So it is about the output can be noisy, and I talked about a simple case where people were trying to program DSPs without considering effect of scaling and round-off noise. The output is all garbage. So yeah, but it is really more about a way of comparing two different digital filters. So we have talked about different structures. The structures look different but have same transfer function. So for example, a direct form digital filter and a transpose form digital filter will have different noise properties. Even cascade, if you take a 10th order IIR filter and organize them as cascade of 5 biquarts or 5 second order sections, and how you place the biquarts in what order, if there are 5 of them, in what order you put them will make a difference. Maybe it is useful to put the pole that is, if there is a pole closer to origin, let's say complex conjugate pole closer to origin, should that be placed in the end or in the beginning? And that's going to make a difference in the round-off noise. So there has been a lot of interest. All these different structures may be perfectly fine in MATLAB with double precision, but when we implement them in fixed point arithmetic, their noise properties will be different.
So is it like fair to say that if we have option for multiple filters, so latency and throughput are one performance indicator. So this is also a performance indicator.
Yes. Round-off noise, scaling, these are all performance indicators, and people have to think about that, yes. And we have seen same thing with different fast filter structures. Some fast filters will be better than others with respect to round-off noise, and that might have something to do with pole locations, for example. So there is interest in studying these things. So anytime the filters, the round-off noise is important for IIR filters. Okay, I mean, if it was FIR, theoretically you can still keep increasing word length. But when it is IIR, you cannot increase word length because it will quickly be unbounded. We can't really, we have to truncate or round. So this is a fundamental property of IIR digital filters. So we have to think about that. Okay. So let's. So these examples are okay for simple examples, but how do we compute the round-off noise in a state space representation when we can describe if we can describe the filter using state space. So what will be the approach to computing round-off noise in the state space using A, B, C, D? Okay, so we talked about the state space representation. The next state xn plus 1 is equal to the transition matrix A times xn plus B times UN. Y is C transpose xn plus D times UN. So, so to compute the round-off noise matrix, W, we basically set the input to be 0. So we set the input to 0. And so to compute W, and W is going to capture essentially that effect. So it's going to capture this effect, which is the noise source variance multiplied by sigma h squared k. So that's what the W, the diagonal elements of the W will capture. So to compute the W matrix, set UN equal to 0, and if I set UN equal to 0, that as disappears 0 times D, this as disappears 0 times B, and then finally what we are left with something like that. Okay, so that's where I believe we stopped at the very end of last class. So that's where we stopped, and we were going to continue with that. Okay, we can now continue with how to compute W matrix. As you can see here, for the same kind of a diagram that I have here, okay, so for the first order system, the transfer function is simply 1 over 1 minus loop gain. Okay. Now in this case, for the let's call this vector E. So this will be a n-dimensional vector. Okay, so so we define the transfer function from the error sources. This is n by 1, so there will be n error sources. So the transfer function will be C transpose times the identity matrix times identity matrix minus A z to power minus 1 inverse. So C transpose is a row vector 1 by n. This is n by n. So this will be 1 by n row vector. Okay, this will be a row vector. So instead of writing 1 over 1 minus A, if it was scalar, I could write A, but for the state space, we write that as minus cap A z to power minus 1 and inverse of that. So that formula that I wrote down, 1 over 1 minus x is 1 plus x squared plus x cubed in the scalar form, also holds good in the matrix form if the matrix is well behaved, namely the eigenvalues are all less than 1 in magnitude. So we can write that again as the infinite sum, which can be written as C transpose plus C transpose A z to power minus 1. Okay. So g of z is z0 plus z1 z to power minus 1 plus z2 z to power minus 2 and so on. That's the definition of Z transform. So we can say that this quantity here is G0, this is G1, this is G2, etc. So we can write like the previous, we defined F as the unit sample response from the input to the state, or F of Z to be the transfer function from the input to the state. G of Z is the transfer function from the state to the output, from the state to the output. So we can say that G of N is equal to one a to power 1, 2 a to power 2, C transpose a to power n, n greater than or equal to 0, 0 otherwise. Okay, so that is going to be this 1 by n vector, 1 by n vector. So we can write this quantity so this 1 by n vector can be written as G1n, G2n up to Gnn. So that row vector, so G1 is the unit sample response from state x1 to the output. G2 is the unit sample response from the state 2 to the output, and so on. Okay, so that is how we define the unit sample response from the state variable to the output. So now we can formally define, just like we defined the K matrix as the expected value of x transpose, the state vector times the state vector transpose. So we can define W matrix to be okay, I will write a better, so I'm skipping this n, but so basically if you think about what we are saying, so the W matrix well, I should say expected value of that. Okay. Well, not really. So G is deterministic. G is deterministic. So we don't need to worry about the expected value. Okay. So what is the W matrix? W is summed over all n, G transpose n, G of n, and that is going to be summed over all n. G was a row vector. Its transpose is going to be a column vector. And this quantity is going to be okay, so there will be cross terms. There will be cross terms. So there will be sigma G1n, G2n, etc. Sigma Gn squared n. Okay, so what we are interested in are these quantities. These diagonal quantities are of interest to us. And that's really what is the effect, of Roundoff noise. So we talked about the effect of Roundoff noise. The effect of E1N, the Roundoff noise at state variable 1 at the output is going to be this quantity here. G1N is the unit sample response from state variable 1 to the output. G2N is the unit sample response from state variable 2 to the output. So we are ultimately interested in these diagonal values. So sigma y squared is going to be sigma e squared times summed over wi for I from 1 to n. Okay, so sum all the diagonal values. There are some technical things that I want to talk about, but for now, summing up all the diagonal values, multiplying by the input noise variance. The input noise variance is going to be some function of the word length w. And we can also call that as sigma e squared times the trace of the W matrix. So the trace of a matrix is the sum of the diagonal values. Okay. So the last thing that I want to talk about is how can we compute W using an iterative approach, and for that we should obtain the Lyapunov equation for the W matrix, and then the same iterative approach will apply for W matrix as well. So how do we formulate the Lyapunov equation for the W matrix? Okay, we'll talk about that. Any question so far? Okay, so W is summed over all n equal to 0 to infinity G transpose n Gn. Okay, so that's W matrix. Okay, and remember that Gn, so the reason it's 0 to infinity is because it's 0 for less than n less than 0. So this is going to be equal to summed over all n. Okay, I'm not writing, but yeah, 0 to infinity C transpose A to power n transpose C transpose A to power n. So that's transpose of this G transpose times itself, which is here. Okay. So so this can be written as then A to power n transpose C transpose is C transpose A to power n. So if I substitute n equal to 0, A to power 0 is identity, so that's C transpose. If I substitute n equal to 1, A transpose C transpose A. If I substitute 2, A squared transpose C transpose A squared. If I substitute 3, A cube transpose C, C transpose A cube. Okay. So now, how do we describe this as a Lyapunov equation? So we can write that as C transpose times A transpose in the left side of the bracket, A on the right side of that bracket. Then what's left inside? So 1A transpose on the left side, 1A on the right side. So C transpose plus A squared transpose, 1A transpose outside. So one more left here. A squared, 1A on the right side. And then A squared transpose, 1A transpose here, C transpose A squared, and so on. And you will quickly notice that whatever is left inside this bracket is nothing but the same W matrix. If it is an infinite sum, that's so the Lyapunov equation is W is equal to C transpose plus A transpose WA. So that is called the Lyapunov equation for the W matrix. How can we compute the W matrix? So we can use the same process, initialize. So instead of initializing F is equal to A, initialize F is equal to A transpose because that's on the left side, and W is equal to C transpose. And then iterate W is equal to W plus F transpose, and F is equal to F squared. So if you do that, and you will quickly see that it will keep doubling. So in iteration 1, it will have 2 terms, iteration 2, 4 terms, then 8, then 16, then 32, and then 64 terms. 64 terms is already a lot, and very likely you shouldn't need more than 5 or 6 iterations, because by then the F will become close to 0. So that's how we can compute the W matrix by the iterative approach. Okay, so this is the Lyapunov equation. Okay, so F and K and W can be computed using iterative approaches within a few iterations because each time the number of terms is doubling, and that doubling becomes a very huge number of terms. For example, 64 to 128, that's a lot of terms to add. Okay, so now let's briefly talk about let's go back to the scaled state, and let's briefly talk about the round of noise of the scaled state space representation. Okay, so we had talked about scaling. So to scale, we defined the scaled state as T inverse times the original state, and we saw that the scaled state can be described by this A scaled, B scaled, C scaled, D scaled, where these parameters can be described in terms of the original A, B, C, D and the transformation matrix T. So this is a linear transformation. Okay, this is a linear transformation. If the transformation matrix is a T as defined here, then the scaled state space has A scaled is T inverse A T, B scaled T inverse B, C scaled transpose is C transpose T, which means if you take the transpose of both sides, C scaled will be T transpose C, T transpose C, and D is the same as itself. Okay. So how do we compute? So how do we compute the round-off noise of a scaled system in terms of K and W of the original system? So that's what we are asking. How do we compute the scaled system? Okay, so to compute that, so we already know that W is given by this quantity here. So W, so let's start with this equation here. So W is summed over all n, A to power n transpose C, C transpose A to power n. So that is the definition of W, and W scaled system. W scaled will be summed over all n, A scaled to the power n transpose C scaled transpose A scaled to the power n. Okay, now let's substitute these values. Okay, so now I can write this as equal to summed over all n. A scaled is T inverse AT. So T inverse AT to the power n transpose of that. Okay, transpose of that. So T inverse AT so T is a diagonal matrix. So T inverse, okay, because these are diagonal matrices, so if I write this transpose to the power n, C scaled transpose is C transpose T, C scaled itself will be T transpose C, A scaled T inverse AT to the power n. Okay, so this is summed over all n, T transpose to the power n, A to the power n, T inverse to the power n. Okay, times T. Okay, let's take a quick look here. T transpose C okay, so I am going to take this T transpose. Okay, let me write that in one step here. T transpose C transpose T inverse AT to the power n. Okay. Well, maybe I should write this T to the power T inverse to the power n, a to power n, t to the power n. Okay. So now, if you think about this, we could write this as so 1t can cancel out with 1t inverse. By the way, I'm assuming t to be diagonal. So if I 1, so I can make this n minus 1. N minus 1. Okay. Same way here, 1t can cancel with 1t inverse. And that will become n minus 1. Okay. So, okay, I think, yeah, so I think there is, so A, B, I probably didn't do this right. Let's take a look. I probably didn't do this right. T inverse A T. Okay, so this to the power n, I believe should be, yeah, some things I didn't do right, I guess. Okay, I think what will happen, okay, so let me just write down some things I didn't do right. I think AB squared is equal to B squared A squared. Is that correct? Yeah. Somebody who took class in linear algebra, right? Yeah. Is that's correct? Okay. So this, when I computed these to the power n, I think I didn't do that right. So okay, A, B. Okay, let's try to see if I did that right. T inverse A T transpose is T transpose A transpose T transpose A transpose T inverse transpose. T inverse transpose, okay, again I can still assume them to be diagonal, and that to the power n will be T inverse to the power n, T inverse to the power n, A transpose to the power n times T to the power n. Okay, I made some mistakes. Okay, so I made some mistakes. Read the book. Okay, it's probably good to take a quick look and okay, read the book. I made some mistakes. I think the final answer that we should have is, let me see if it's in the book. So, okay, let me just write down. So anyway, this, yeah, work this at home. Okay, so you should be able to show that this is equal to T transpose WT. Okay, so W scaled can be described as T transpose WT. Okay, there is some mistake here, but if you correct that, I will see if I can correct that after the class. Otherwise, it should be that quantity. Okay, so I wonder though if it is somewhere in the book. Yeah, it probably is, or I think I think it's not in the book because it's given as a homework problem at the end of the chapter. Okay, that's the reason I didn't. Yeah, okay. So Okay, I will try to see if I can just give you a clean proof of that. So, so if T is a diagonal matrix, remember the diagonal matrix that we were talking about last class with T11, T22 as the diagonal elements of the T. So that's what T is. So T is T11, T22, etc. So that's a diagonal matrix. So you will see that the W scaled II, the ith diagonal element of W scaled, is going to be TII squared times WII. Okay. So what did we define? How did we define the K matrix? So we saw that the T was chosen in order to make sure the K-scaled matrix was identity. All the states were orthogonal. Okay, that means the covariance matrix of the state variables of the scaled state space system is a diagonal matrix. And for the scaled matrix, it's not only diagonal, it's all one, so it's identity matrix. And that was possible by selecting TII to be square root of KII, which means TII squared is going to be KII. So if we have computed the K and W matrices, then we can compute the round-off noise of the scaled system in terms of the K and W elements of the original system without computing the T matrix at all. So the sigma y squared scaled is going to be sigma e squared times sum of these diagonal elements. Okay, so that is the round-off noise of the scaled system without computing the transformation matrix T. If we have already computed K and W, then we can just take the product of the diagonal elements and sum them up. That would be proportional to the round-off noise of the scaled system. So there are certain technical things that I wanted to talk about. So in order to describe the state space description, okay, so basically every round-off noise source, should be a state variable. And many times that is not the case. Okay, so so for example, let's take a simple direct form digital filter. Okay. Okay, this is a simple direct form digital filter, and if I want to compute using K and W matrix, after every multiply add, I should have a round of noise source E1, E2, E3, and that means at the output of that, that should correspond to a state variable. this should correspond to a state variable. Otherwise, it won't work, right? If we are going to compute the W matrix and every round-off noise source, after we do the multiply add, should correspond to a state variable. Next state doesn't matter, still a state variable. And so in the direct form, we have to apply a pipelining cut set. So basically, introduce a pipelining cut set so that these become state variables. Okay, now in this system, if you look at it, we have 1, 2, 3, 4, 5, 6. So there are 6 states. Okay, and even if okay, 6 states, let's say. However, the sigma y squared is only going to be sigma e squared times w11 plus w22 plus w33. So if I call these state variables 1, 2, 3, and then 4, 5, 6, 7. So what I'm trying to tell you is that W may be a 7 by 7 matrix, but the only diagonals that we are interested in with respect to round-off noise are these 1, 2, 3, W1, W2, W3. These, although these are state variables, are not associated with any multiply add round-off noise sources. So when you compute the trace of the matrix, don't take these elements. That's what I'm trying to say. Okay, so that's kind of one thing. And in a way, so think about by adding these two, actually one more, technically one more, by adding these 3 pipelining cut sets, it really is not changing the round-off noise. So if a certain transfer function, let's say that I have certain transfer function from an error source E to the output, and that sigma h squared n, I can compute that. And then if I pipeline this by m pipeline stages, and then let's call this h prime z, and sigma h prime n squared is equal to sigma h squared n. Okay, why is that? Because let's say that this was hn was h0, h1, etc. H prime n is going to be 0, 0, 0, okay, and then h0, it's simply going to be delayed by those many samples. So these are going to be m zeros. So if you take the square of these, we are just adding 0 squared times m. So that sigma h prime squared n is going to be same as that. So adding these pipelining cut sets does not alter that computation of sigma h squared n. So it doesn't affect the round-off noise. That's kind of one property. So we have to think about another property, which is sometimes we may have filters. So let's look at this filter here, which is some kind of a lattice filter, and I'll start talking about this next class. So for example, if I look at this multiply add, I need to have a state variable here. State variable here. This multiply add, I need a state variable here. Multiply and add, I need a state variable here. So this one is perfectly fine. We multiply something, multiply here, add, so that's called number 1. So that's state number 1. State number 2, state number 3, which are perfectly fine, but in order to use the computer to compute this W matrix, the correct way to get these as state variables is to use replace each delay by 2 delays. So think about that as interleaving. Replace each delay by 2 delays and retime. So remove one delay going left and put them to the right. And that's what happens if we do that. Moving one delay, so first we interleave, means replace each delay by 2 delays, and then retime at these cut sets. And now this multiply add became a state variable. So every multiply add is now a state variable, number 1, 2, 3, 4, 5, 6. And again, my point of illustrating these is, although state variable number 3 is part of the round of noise, W44 is not part of round of noise. So this delay is not associated with any multiply add. So do not take W44 diagonal element and add them to the whole diagonal elements for computing the round of noise. Pay attention which state variables correspond to round of noise and which diagonal elements should be added. So that quantity should not be added. So a filter with non-state variable node has to be converted to a state variable node by using either pipelining or by so-called two-slow transformation followed by retiming. If we have a transpose form FIR, then we don't need to pipeline anymore. These are already in state space form, and you can just compute the W matrix. Okay, that's quite a lot, and so that really completes chapter 11. We will start chapter 12 next class on design of lattice filters and their pipelining properties. Okay, so your graded homework is here, so don't go away. I will hand them out. We will also have office hours, so if you have questions, we can discuss them as well.